is on hands-on demonstrations. Thank you, Maria. So with that, Judy, I'd like to think you're starting on our hands-on demonstration.
Right. Okay, so let me share. Sorry, I need to get the right screen. And then Ron, I'm going to give you remote control for later. Okay. Everyone seeing the slideshow okay? Are we good? Yes, no? Yes, okay, awesome. All right, so some hand-on demonstrations and other visual aids. So we've kind of titled this as like low or no budget ways to help your students understand behavior. So I like to say like everything in STEEL can be described with foam and or paper, or in Ron's case, broomsticks and friendly people. So you'll see what we mean in just a little bit. One thing that I would suggest when we're back in person and have that awesome exhibit hall at the STEEL conference is collect STEEL bits, right? Slices of W shapes, bolts, other things. So maybe they don't really demonstrate behavior, but they're always good pass around. Or as shown in this photo here with one of my former colleagues, Dan Morello, and student Mado Parikh. Sometimes I like to take a W shape and have students measure the different dimensions and say, do they think it's a compact flange or a non-compact flange, or let's go back. Do they think it's a compact web, for example? And then just even things like, just a steel bolt. I think there's something to passing around a steel bolt and just feeling the weight and just what it looks like. And even things like little punches, right? So, they're always demoing these things in the exhibit hall. And so you can talk about, right, the piece that got punched out, what the hole looks like, and how that impacts some of the things that we do in our calculations. So the list of some of the demos or visuals that we'll be talking about today are here. The ones with asterisks beside them do have instructions that can be found on the AISC Educator forum. So do check those out if you're interested. So let me just start kind of at the top of the list with some foam beams and beam buckling models. And credit for these two different sets of teaching aids goes to Scott Sivian. I don't know if he's still on the Zoom meeting, but I saw him earlier. So it gave really awesome instructions for assembling these beams out of foam, and as you'll see later, some other materials. So I use these all the time. Probably the ones that I use the most often are just like the rectangular one, and of course, you can show plane sections remain plane, and the tension and compression that we see in the cross section for flexure. The W shape, I probably use even more. So first of all, it's very huggable. It's really fun to carry around with you. But I use this anytime, like as in the picture, if I want to show weak axis buckling, or if I want to kind of, anytime I need kind of a 3D representation to help the students, whether it's like side sway or otherwise, or even just talking about flanges versus web and things like residual stresses, and kind of talking about, what's going on through the cross section or through the member. Some other cool models from Scott are these beam buckling models that are made out of overhead transparency and packing tape. And so you can use these to demonstrate. So the instructions show what proportions to use to get one that will show flange local buckling pretty well, one that shows web local buckling. That one's a little harder to visualize, at least with my fabrication skills for my beam, and one that shows lateral torsional buckling pretty well. So this one here, I don't know if we'll be able to see. It's a little bit pre-buckled now. Let's see. But if you can see when I try to put it into bending, I don't know if you can see the flange, the top flange in particular is doing some local buckling there. And then this one for lateral torsional buckling, you can see it's a little different in the cross section. And so usually what I do is I just try to put this into kind of pure bending, and sometimes it's a little easier to see if I hold it horizontally. And you can see just under pure bending, it's just kind of that compression flange is just kicking sideways. And so in person, when we're in person, I kind of show at the beginning class, but then also pass it around so the students can kind of test for themselves. There are also some various great videos online. So these are some sort of small scale tests linked from this playlist that is also linked from the AISE Educator forum. So some really neat lateral torsional buckling and flange local buckling, but also things like, I'm not sure it's showing here, but different column tests that they did. And I believe lower on the playlist, I believe there are some bolt tests where there's bolt shear and bolt bearing failures. So a nice collection of different videos that might be useful. And then getting into things like effective net area. So, you know, I found, at least when I started teaching steel, I felt like table D31 was kind of like this mystery to the students as far as, you know, what's going on here, you know, why do we have these different things going on with effective net area and these shear lag factors. And so I just want to highlight a couple of things for case 2 and case 4 of some hands-on demos that you could use. And so supplies here, just some paper, some cardboard for connecting on one leg of this paper angle at one end and connecting to both legs of the paper angle at the other end. You know, some tape to connect it all together, and a marker, optional, right, if you want to show connections there. And I'm going to just kind of show parts of a quick video here. This is a link to a playlist that has some different, the different collection of videos that I'll be showing today and some more. Let me switch over here. All right, so are we seeing the playlist now? Yes, no? Okay, wonderful. So this is the playlist, and again, it's linked. You can get to it with that link on that slide. These are more fun to do in person, but you are welcome to use these videos if you would like to. I caution, they're very, very homemade, and like they're not very professionally done, but if you find them useful, that's great. And so what we do with this is, you know, kind of talk through and introduce the students to what's going on with this paper angle and then, you know, where it's connected and so on. And then you have to make sure your helper understands to hold on to both legs at this other end. But in any case, what you notice is when you tap on each of the legs at the end that's connected on both legs, you can really feel the tension in both legs of the angle. And then as you move towards the other end, right, in that bottom leg that is connected to the quote unquote gusset plate, you can still feel the tension in the paper angle. But as we move from the left end to the right here, then at this other end, right, it's nothing, it's flopping around, right? We don't have the tension stresses in that the leg of the angle. And I should give credit to Rob Connor at Purdue for this particular demonstration. All right, so let's go back to, if we look at case 4, so the case where, let's say on a plate or other connected element, we just have longitudinal welds at the end here, and we have some aspect ratio between the width of the plate, for example, and the length of the welds or the length of the welded connection. And we have this new part of that shear lag factor equation, which, you know, graphically we can see here with respect to that portion of the factor with respect to the L over W, that aspect ratio. And to help the students kind of understand what's going on here, why we have this shape to the curve here, we can do kind of a very simple demo just using like patchwork quilting fabric or something similar to that. And when I had to do this remotely, so usually I should mention, usually I have like at least 3 people doing this, like one person on trying to be uniform tension, one person trying to be the welds at the other end, and then me kind of talking through the demonstration and doing some tapping. But when we were remote and I just had myself and my helper here, let me switch back to the videos here. Oh, come on. Oh, that didn't work. Hold on, try again. All right, I added a mixing spoon. And so what you'll see here is at the end, that's the uniform tension across the cross section. If I can get the right part of the video here, is I rolled the fabric around the mixing spoon. So I could just basically grab onto that spoon, right? Or anything like with a long handle. So I could just grab onto the spoon with one hand and have fairly uniform tension at the end. And then here I'm talking through the aspect ratio between the lengths of the welds, his hands there, and the distance between the welds. And as we're initially applying tension, we can kind of look at how the stresses are distributing from the cross section with uniform tension over to the section where the welds are, right? And we can see that that portion where I'm holding onto there or pointing out there, there's really, right, there's not a lot of tension there, right? It's just kind of flopping around, as opposed to where there is some good tension in the plate here. You can kind of feel it in the fabric. And then of course you can change it up and change the aspect ratio between like length of weld versus the distance between the welds, and describe and see how that is different than the previous case. Right, so we have something like that going on. And then go back to this presentation. All right, so some other models that might be useful to use. So for block shear, so we do have those great animations that we showed earlier, but I also have these kind of thin craft foam models. So craft foam sheets, paper fasteners, a hole punch to make bolt holes. And so you can see we have kind of some same bolt pattern, but some different possible block shear modes. And usually what I do is, even if I'm in person, usually I take one of these models and I kind of lay it down flat on the document camera. And then I just kind of, well, first I talk about it, right? And I ask the students what they expect to see, or talk about the different shear and tension areas. And then we just kind of pull it apart and we see pretty clearly, right, what stays behind, right? What stays behind and what gets pulled away as far as that block shear mode. And similar discussions for these other modes that we have here. And we talk about, you know, what's different if we have different bolt pattern and so on. And that sure kind of helps set things up for when we do some different calculations and some different examples. All right, so I think earlier there was a picture of a paper column activity at this workshop a few years back. And so very low tech, easy demonstration of local buckling. And so there's 2 columns that are sort of this kind of size, right? And just very easy, some folding and then taping together. One out of cardstock and one out of regular paper, although with the current manual, if you can get 24-pound paper, it's easier, it works a little better. And then another column that just same amount of material, 1 piece of paper, but as you can see, fold it differently to make a smaller cross section. And so as you can see, what we do here is we use our manuals to load test. right? So I just bring a bunch of supplies, paper, cardstock, and tape to class, and the students have their manuals, and they're working in groups of 3 or 4. And they're doing assembling these columns and also learning about careful fabrication, right? Trying to get the top and bottom flush. And then they do these load tests on these different columns. And then what you can see is, I think you might be able to guess, right? These two do fine as far as supporting the load. And this one doesn't fare quite as well, right? In terms of supporting the load. Right, and so that's kind of fun. I always enjoy the students' faces when they walk into I usually do this in the lab session, so when they walk in and they see all these materials on the tables, they're like, what is this? It's like kindergarten again. So it's kind of a fun departure from kind of the regular class activities. So when I do this remotely, and I may or may not do this when we're back in person, is I did a discussion board assignment where the students individually, or they could do it in groups. They did these tests on their own at home, and they posted their predictions for what would happen, as well as photos and or if they preferred a short video clip of their load tests. And so what I did on the discussion board is when I posted the assignment, I posted an instruction video with that assignment on the discussion board with things about like how they were supposed to fold the paper, being careful about their fabrication and being careful about loading, especially that one that gets the local buckling. And then after all the students had submitted, I did post the results of my own column test. And then what we did is, after the students posted their predictions and photos or short videos, other students reviewed and, they would like their favorite post from their classmates. And the one with the most likes was the one that we shared and discussed in class. All right, some other things like if you're talking about earthquake loads and acting on your steel building, kind of a shake table demonstration. This particular one I did, this building on the right is very similar to the case study building we use in class. And then a taller, skinnier building here. We also played with mass and adding Play-Doh and just looking at the responses of the different buildings. The materials I used here was a girder and panel set. I think originally from the 50s or 60s. I got one of the original sets from, I think, eBay for Christmas one year, best Christmas ever. But in any case, as far as if we can just take a peek at the video here. I don't know why it doesn't want to do that. Oh, come on. All right, there we go. All right, and so when I can, I do borrow from one of my colleagues a little tabletop shake table, but you can just do this with like a wooden base and with just like people power. And so we talk about the what we expect from these different buildings as someone is acting as a, oh, come on. Apparently I did a lot of talking on here. Someone acts as an earthquake, and we talk about the different responses of the different buildings and how that relates to the fundamental period of the building and the frequency of the ground shaking. Then we add some Play-Doh mass and also then talk about what we would expect in terms of the different response and how that's realized. I do have a problem with uplift with the taller building. So as you see, at one point, we take off the taller building so we can look at the ground shaking that it takes to kind of activate this shorter building here. All right, so that's kind of a fun way to get some visuals for some of our earthquake loading. And somewhat related to that, there's some really wonderful videos out of Princeton. So here you can see a video clip with Maria Garlock and also demonstrating earthquake loads and also things like shear walls, moment frames, pin connections, right? Pin connected frames versus moment frames. So a really great set of resources here at this URL. And then I believe below this video, there's also a nice supply list if you want to make your own sort of demonstration that looks something like this. Simple but very effective. Some of my colleagues made these very simple single degree of freedom models here, ones with like springs, same height springs, but different masses, and then same masses, but different height springs. And so those are always very simple and effective as well. And then I think I just have one more that I wanted to share here. So as far as built up compression members, I find that sometimes that's a little hard for the students to get. And so again, very simple, easy materials here. I don't know why it never likes to do it when I do it first. Okay, third time's a charm, I think. Come on. There we go. All right, so to try to, like, so if you have angles, right, double angles stitched together for a brace frame member or something like that, and just kind of explaining the role of the stitch bolts and how that can affect what we see for the compression capacity. And so first, just 2 cardboard strips that are you know, not even attached together, right? They're just laid one atop another. I'm just trying to apply uniform axial compression, and you can see how much the buckled shape and what that looks like over this grid paper here. And then we take the same 2 size cardboard strips and we glue them fully together. And so they're fully bonded, right? Kind of an idealized case here. And similar axial compression load as the first one, it doesn't barely budge. And then I put a little more force on it and you can kind of see the buckled shape here. So definitely stiffer, right, when it's fully bonded. And of course we talk about the reasons for that. And then 2 cardboard strips, same size, but with these stitch bolts, right? Very fancy stitch bolts here with the paper fasteners. And then do the similar load test here. And then what we can see here with a similar loading as in the first case, not quite as stiff as the second one for sure, but stiffer than the first one, as you can see from the buckled shape here. All right, so those are just some of the
Hey, Judy,
different, yeah.
you, leave that one open for a second. So I did play with this one, and there's a really cool addendum to this that's kind of fun. And so when you went with the glue, instead of gluing the full length, just glue the first inch or 2 at each end.
Yep,
and
yep.
like with the paper clips, just 1 or 2 paper clips at each end, and you almost get the same capacity as the full. Right. It's kind of a neat little sidebar.
Yeah, great point.
Yeah, that's a cool lamp. I really like these.
All right, great. So now I get to hand it over to Ron.
All right, so Judy was demonstrating a few examples, several examples, and she's amazing at this, of you know, these handheld devices that she creates and are just fantastic at demonstrating behavior. Mine are going to go a little bit more in the human form. And so maybe not ideal during these COVID times, but I do think some of them are kind of fun, at least to get the students involved. But the first one, not as humanly, but I talk about the behavior of steel structures. And of course, one of the key things about steel is its amazing ductility. And so I'd like to show that using this following example. So now, depending on where you're located in the world, it might not be perfect for you to use the Pittsburgh Steelers football stadium. The students might get up and leave, but in our area, you are either an Eagles fan or a Steelers fan. So what I tend to do is try to explain to the students, on the upper left, they see this stress strain diagram all the way back from solid mechanics when they did the lab. And it just demonstrates the amount of ductility that steel has, but the curve is not to scale. And so I try to do is put it to scale with reference to the football field. So I'll try to do that in words, and then we'll go to the next slide. Okay, Judy, so, whoop. All right, no problem, let's start here. So this is actually what it looks like. So if we were to start at a stress value of 0, with a corresponding strain at 0, we would be at the 0-yard line. If we were to apply enough stress or enough strain to get the material to just yield, reach our yield point, that would actually be the 1-yard line. So we've only advanced, for the full football field, we've only advanced 1 yard. Then to get to strain hardening, we would advance 9 more yards or get ourselves to the 10-yard line. And then to really demonstrate the amount of ductility that you have, this thing does not rupture until you travel in the football field lingo 90 more yards. And so there is just a phenomenal amount of ductility in steel. And we can take great advantage of it if we know what we're doing. So I think with that one, so I could certainly show the students connections that were not ductile, lots of fractures, but if you proportion the connections correctly and according to AISC guidelines, you can get full plastic hinges as being shown in this picture here by a graduate student down at the University of Sydney, that a well-proportioned steel connection can have an amazing amount of ductility and take advantage of that ductility in steel. On the other hand, just because you have ductile steel does not mean that you'll be able to get the performance of a connection like that. And, we think back to Northridge and those type of problems that we've had in the past, but those are behind us now. So, all right, next slide, Judy. Okay, so one of the concepts that I try to demonstrate to the students that they sometimes have trouble with is the idea of residual stresses. And so many of you are aware of this, but I'll just sort of recap so you're all up to speed. But effectively what happens is the section is rolled and into an I shape, let's say, and then it's put over on the side and to cool. And when it cools, when it's super hot, it doesn't really have much of a modulus elasticity. And for a while, the whole section cools pretty uniformly and starts to shrink in length. But eventually, the areas that have the most surface area, like the flange tips, they tend to cool before the red spot there or the flange web intersection. So once those flange tips sort of cool first, their modulus sets up pretty close to the full E value, where the hot zone in the center, its E value is still pretty small. And so it continues to want to contract. So we get into this sort of fun situation in which by the time the whole cross section has cooled, the web flange intersection is in tension and those flange tips are in compression. And it's not the most ideal place to have compression because when you have minor axis buckling of this column, you've got some zones that are being heavily compressed due to the force, and there's already some compression there. And so I try to, also relate this to the students of, you go to the store and you buy a bag of potato chips and you open up the bag and, there's hardly any chips in there. It's sort of similar with steel. You purchase an I shape and by the time it arrives at the site, there could be on the order of 15 to 20%, maybe even more residual stresses in there, and you haven't even put any load on there yet. Always important to remind the students that if it's rotary straightened, a lot of times these residual stresses are pulled out, but if it's certainly a welded or built up shape, they're often not pulled out. So to make this real for the students, what I tend to do is have 3 students and 2 broom handles. And the only thing that takes a minute for you to get your bearings is the sort of the orientation of the thing. So I have 3 students there. Their t-shirts vary. 2 of the t-shirts say flange tip. They're sort of on the outside. And then the center student has FW on their shirt for flange web intersection. So the students start with their hands pretty far apart, holding the broomsticks. All 3 are holding the broomsticks. And their orientation is such that the length axis of the member is the sort of length axis of their arm going from their hands going from one hand all the way across to the other. So if you got that down, then we sort of say, okay, students, let's imagine we have 3 students here. You're all super hot. You've just been rolled, and start cooling. And at first, what you do is have all 3 students sort of pull their broomsticks very slowly and just a small amount towards each other. All right. And then you say, but the flange tips, the students on the outside, suddenly are starting to cool more quickly and sort of firm up, and they're going to sort of lock up. So I think if we go to the next slide, there we go. So the flange tips now are blocked up. They're at full E and no more contracting. But the flange web intersection is still hot and continuing to try to contract. And when it does, it's of course pulling inward. And you sort of end up with the broomsticks sort of bent to show what's going on. And yeah, thanks, Judy. So if you sort of do the mechanics now, the center portion, which is pulling inward, is of course in tension, and the flange tips, which are both pushing outward, are in compression. But nothing's moving. The whole thing is in equilibrium. And so that's sort of a demonstration then on how things work. And then of course you can have some fun. I think one more click, Judy. Does anything happen? Oh, no, they're not going to behave today.
Sorry, I don't know why it's not working.
But
you have to describe what they'll see.
No, I just took 3 days out of my life building that. No, but what will happen is the students pulling in and out. I had a little animation of this, but no big deal. All right, so that's the first one. And if we were in person for our faculty workshop here, we would have 3 of you come up, as we have in years past, and do this demonstration, broom handles and all. So great, thank you. Next one is shear lag. Shear lag sort of enters the conversation more on the lower right when Judy was talking about computing the effective net area and showing portions of the section that are fully engaged and others that are not. This is all happening because of this concept of shear lag. So if you're not familiar with shear lag, we sort of see it quite a bit in buildings. So on the left, the blue square there, if there's no shear lag, then what's going to happen there is the wind load tends to cause the building to bend, and we sort of develop the MC over I stress distribution that we're showing. On the other hand, if we have shear lag, the web still sort of ends up pretty much in an MY over I, but as the stress is moving from the web into the flange portion of the building or the faces of the building, there's enough shear deformation that the columns towards the center of the flange portion are not doing as much work to resist that overturning. And so there's an uneven distribution of the normal stresses due to the shear lag effect. And you can see this, we'll use the upper right as the example, but in the lower left, if there was no shear lag, okay, which is pretty popular with a fairly heavy, stocky cross-section. You would have this normal stress distribution that's being shown in the lower left with no shear lag. On the other hand, if it's shear flexible, let's say, and you're going to get some shear deformations occurring, then that normal stress distribution that you would expect of being uniform will not be uniform. There'll be higher stresses near the flange web spots and lower stresses out in the center. And so you see this in other places, for example, composite decks or something like this where the beams are spread out fairly far. You need to sort of think about that. So the example that we're going to do, we need actually 6 students. And we're going to run 2 cases with these 6 students. The first case is what I show on the left there, in which you know, we have a pretty stocky flange. And so we're just going to be modeling the shear lag effect within the flange. So imagine a small BF to TF or a fairly thick flange thickness, let's say. So there's not a lot of shear flexibility there. And the second case is, you know, in our case, what we're going to do is increase the flange width significantly, or if we had a really slender, slender cross section, or a large BF on TF, a thin section. So those are the 2 cases we're going to do with the students to demonstrate this. All right, so here are our 6 students. They sort of look like ducks here, but they're all lined up. Oh, I'm sorry, 5 students. I don't know. Oh yes, we have a 6th student coming. But we have the 5 students all lined up. They're all sort of next to each other. The students on the outside of the flange tips, and the student in the center is the flange, web flange interface. All right. And the first case is with no shear flexibility. So these students, all 5 of them are pretty close, and usually what they do is sort of wrap their arms around each other, and they've got a significant amount of shear stiffness between each other because their arms are all wrapped around one another. And once we've got everyone lined up, then we introduce the web. And the web has some shear stress, has some normal stress that it's going to try to transfer into the flange. And so it pushes at the flange web intersection. And because all of the students representing the flange are all you know, got their arms very tight against each other, there's really no room for shear deformation, and all the students sort of bend over at the same time. So that's a good uniform distribution of normal stress. And the next step, what we do is now have the students spread out. And so they spread out really far from one another, just far enough so that they can at least hold hands or intersect hands. So now we have quite a bit of shear flexibility in between them. Orientation the same, outside students is the flange tip, inside student is the web flange interface. And we deliver the web, and the web now delivers this normal stress into the flange at the flange web intersection. But because the flange is so flexible with respect to shear, maybe the students closest to the flange web intersection might bend over a little bit, but the students way on the far outside, they're just not doing anything to resist the stresses that the web is inducing into the flange web intersection. So we're getting quite a bit of shear deformation between the 5 students that are up there. So that's a physical demonstration of shear lag. Here we are at one of our previous workshops, and this picture is kind of crazy. Well, one, it's just demonstrating when they're case 1. So we've got our faculty all happy and hugging here. But if you actually look on the faculty shirts, there's a slide showing the shear lag from the previous faculty workshop. So it's like a kind of a bizarre Escher scheme, picture on top of a picture. And here they are demonstrating the situation. They're not Greek dancing. They are actually demonstrating the shear flexible situation, and I am the web getting ready to transfer stress into the shear, into the web, into the flange at the flange web intersection. So that's our demonstration there. I think this is the last one I have. I'd like to talk about system behavior and leaning columns and the P delta effect. So let's start with the leaning column concept. Again, just revisiting it with you folks. And if you look to the right, there's a frame. We're looking at its plan view. The frame has a core that's intended to resist all the lateral load. And then around that core are all these gravity columns with just pin connections at their ends. So all those, so we have 4 columns in the center, and they're all happy. But those 20 gravity columns, if it wasn't for, and the floor diaphragm is participating as well, but if it wasn't for that rigid core, all of those gravity columns would just fall over. There's nothing holding them up. And so I'm trying to demonstrate that to the students, that each one of these gravity columns is actually exerting. And so I'll flip to a more simplified version of this concept shown at the bottom, where we have, oh, if you could back up one, yeah, we're at the bottom where we have the portal frame, so that's the core, if you will. And then to the right, we have 4 leaning columns. And what I'm going to do is introduce a leaning column, and we're going to see how much each one of the leaning columns increase the load on the portal frame. All right, so to do this, we'll need 4 students and a bathroom scale. We start off, of course, with the bathroom scale at 0 and pushed up against the wall. The wall is our core. And so at this point, we have 1 student, and that's 1 leaning column. Now, it's important that the student leans and that they're only on 1 foot. All right, so if you have them on 2 feet, they're going to develop some moment themselves. So let them be on a pin support. And if you follow the scale, there's a little red arrow. And as Judy starts to increase the number, you can see, all right, we've increased the load on the scale. We now have 2 students, 2 leaning columns, and against the wall, 3 leaning columns. More load should be recorded on the scale. And then 1 more, and we've got the 4 leaning columns, and each one exerting some force. So, and you can start to do sort of interesting things. You can use sort of the mechanics of equilibrium and sort of establish how much force each student is applying, and then the total, and that should be pretty close to the reading on the scale. So kind of fun stuff there. Again, everybody needs to be on 1 foot. Oh, here we are at a previous AISC workshop. Now, just to make sure things are a little bit more unstable than they need to be, AIC introduced beer and wine, but to increase that destabilizing effect. But you have to be a little bit careful. The students really kind of enjoy this one. They really start to lean, so they have a large initial imperfection. And what will happen sometimes is they'll buckle out of plane. And they're on 1 foot, they're all leaning, then somebody falls out of plane, and then they all fall out of plane, and then you're at the infirmary. But no. So it's kind of fun. And the last simple one is just what I call the backpacker example. You start with a student that doesn't have a backpack on, and they get nice and happy with their feet and stable, have their feet together. And then another student will try to push them, and that's not too bad. They can resist pretty well. But then you fill up the student's backpack with every book in the class, or have somebody else get up on their shoulders, and now you have a lot of weight on the column, and now the person there starts to push laterally, and you'll see just how unstable that column is, and that's all a result of the P delta effect. So those are my, and keep in mind these are all trained professionals, so no, I'm just teasing you. Oh, it looks like I have one more, live loads. I thought this was sort of interesting for you to do. I've done it for years, and then I found out that they actually had a luncheon or something. They decided to do it at something conference in Hager. But if you sort of walk around, the text is a little bit small, but what you do is you sort of lay out, in their case, they did an 8 foot by 8 foot square. And then you start to put people in it. And so here they have 12 people in photo 1, upper left, and that's, it looks like 5.3 square feet per person. You have to get the people's weight, and you're about 30 pounds per square foot. Photo 2, they've increased the number of people. They're up to 45 pounds per square foot, 60 pounds per square foot. So now you're starting to get to the design loads that you may find in ASCE 7 unfactored. And so we're at 60 pounds per square foot. 30 people in that 8 foot by 8 foot square, we're at 76 pounds per square foot. And then finally, You have 36 people. It's very uncomfortable. Everybody is literally on top of each other, and you're just shy of 100 pounds per square foot. And so then you can ask the students, look, this floor was only designed for, say, 60 or 50 pounds per square foot. How come they haven't gone through the floor? So and then everyone sort of scrambles. Oh my God, what if we did? But anyway, so that's I think those are my examples. Yeah. So thank you.
Yeah, thanks so much. That's great. And then just, I guess, maybe a quick question or two, but also in the slide set, you might notice that there are some different other visuals and suggestions for hands-on demonstrations that were suggested from the 2018 workshop participants. Back to you, Christina.
Okay, thank you. All right. Okay. All right, so next we'll talk about teaching aids. AISC provides many free resources that educators can use to teach steel design. And you can find these files at www.aisc.org/teaching aids. And you can browse by curriculum. We also have some interactive applets in addition to PowerPoint presentation files and any other files that you see in there that you want to use, such as images. And you can use those for free in your classes. So if you're not familiar with them, we really highly encourage that you browse through those. In 2019, we awarded grants to several educators to develop new teaching aids. And we tried to really focus on higher tech teaching aids, not just PowerPoint slides, and teaching aids that would help help students visualize. So you'll hear from 4 of these educators today that developed teaching aids for us, and they've each provided a short video introduction to their new teaching aid, explaining how to use it. These will be posted on the website along with their teaching aids. Hold on one second.
Hi everyone, my name is Rachel Chicky. I'm an assistant professor at the University of Cincinnati, and I've been working with AIS.
It's not pausing. Okay, sorry about that. So the first one is Rachel Chicky from University of Cincinnati.
Hi everyone, my name is Rachel Chicky. I'm an assistant professor at the University of Cincinnati, and I've been working with AISC for the last year, working on some teaching aids related to steel connection design. I've actually done 3 different modules. I'm going to focus on just one today, but I wanted to mention the other ones as well. Hopefully coming soon will be some PowerPoint slides that you can use for lectures related to steel connection design and detailing. And then also some videos and an activity using QNect, which is a connection design software. So students can change parameters, learn about the constructability of connections, and do it through a video, kind of more hands-on activity. What I was asked to talk about today is our module that just became available, which is 3D printed connections. So we've actually 3D printed 4 different types of models, and I'll show you a few of them here. And then there are 2 others that are still being developed. If you'd like them, I can share them as well. So we're talking about models of about this size. So this is showing a column with 4 different kinds of possible shear connections: single angle, double angle, shear tab, extended shear tab, and then we have the corresponding pieces that you would then connect to it. We are using magnets to represent bolts. And then anything that was welded, so for example, in this case, a welded bolted double angle connection, the welded part is just printed as part of that column. So it comes out in that way so that students can sort of see, okay, if I want to connect, if the piece is welded to the column, what does that mean about the piece that needs to frame in and connect? Well, in this case, I need to cope that bottom flange in order to make this something that can be erected. Okay. I acknowledge that not everyone has direct access to a 3D printer, but most universities will have some kind of makerspace within your college or within the overall university where you would be able to pay some amount to have these things printed. Each piece, the bigger pieces take, for us, it took about 6 to 8 hours for the column, but like the pieces like the beams take a couple hours to print. Takes about half a reel of material to print. And if you buy all the magnets, the whole cost of all of this is less than $50. We also have a beam to girder connection. I'll show you the electronic version of that. We have a bolted flange plate connection to talk about moment connections and be able to explain the difference in a moment connection versus, you know, just a shear connection. And then also an end plate moment connection. And so you can take the pieces apart where there are bolts. You know, the column, the beam would have this end plate on it, and then you would show basically how that gets put together. Let me show you some of the resources here that are available for this. So we have created a README file, which really provides all the information, hopefully, that you will need. Feel free to reach out to me or to University Services if you have any questions. But it'll walk through the file structure, the basics of 3D printing requirements. There's nothing too specialty that needs to happen in terms of the 3D printing, but we've provided our basic standards, and anyone who has any knowledge of 3D printing should be able to print these without too much trouble. We've provided some suggestions of supports and things like that. And then the frequently asked questions, talking through, you know, what if you don't have access to a printer? What does it cost? Those sorts of questions. And then talking points. The whole purpose of this is to be able to use it in a class and to be able to show why one option might be a better option than another. And so these would provide some talking points as you're working through with each of these connections. So you have access to it and have some good things to talk about in class. Within the file structure, so each connection, outside of the README file, we have the actual file that we use to create everything. So if you wanted to modify it in some way and create another connection, you're welcome to do that. And then within each connection, there are just photos of it, so you know what it will look like. And then each piece. So we've labeled each piece. So in this case, this is the girder that would be printed in the beam to girder connection. And it's already been oriented in the way that we would recommend you do the printing. There's no scaling or anything needed. You just need to set it up with the basic printing process and go ahead and print it. So we have each piece ready to go for you, where you just need to send it to the 3D printer, basically. Here you can see that we've coped part of it, so you can talk about coping with beam to girder connections. And then we've also created the beam to girder virtual, which is just combining them together, that if you didn't have a 3D printer but you wanted to be able to you know, still show these things, you can provide these to students. So it's like an electronic version of the 3D printed connections. You wouldn't print these pages or these files, but it's just a way to make them available to you. I just want to mention the cost at the bottom. It has no significance. It does not cost $215 to print this. This is, we don't know exactly where this gets generated from, but it is not a cost that's a cost of the connection in the real world or the 3D printed connection. So just make sure you don't pay attention to that. And so that's really it. We provided, again, 4 different connections with 2 others coming, where it just basically gives you the opportunity to pass it around, point out certain aspects of constructability, and hopefully make connections a little bit more understandable to your students. I hope you find it helpful. Thanks.
Okay. So that was the first teaching aid. That was a 3D printed connections by Rachel Chicky from University of Cincinnati. We've actually had some people test it out already at different universities, and they're really quite easy to make. So our next teaching aid, the second out of the 4 that we're profiling, is the Structural Fire Engineering Teaching Modules produced by Erica Fisher, who's an assistant professor at Oregon State University.
Hello, everyone. My name is Erica Fisher. I'm an assistant professor at Oregon State University, and I'm here to talk to you about the structural fire engineering teaching modules developed for the AISC educational resources. Just a little bit of background on these teaching modules. Structural fire engineering is the design of structural components and frames to maintain load carrying capacity throughout a design basis fire. The purpose of this is to design our structural components to deform such that compartmentalization is not lost. Compartmentalization is what's going to keep the fire from spreading horizontally across a floor plate or vertically throughout the building. However, this concept is not taught in typical undergraduate civil engineering curriculum, not even with the prescriptive approach. So this is really the motivation behind developing a lot of these modules. Each of these teaching modules has 3 different parts to it, or 4 different parts, depending on how you look at it. The first part is supplementary material. Just as this isn't taught in any civil engineering undergraduate curriculum, or very few of them today, a lot of you actually didn't receive this education either. So we thought it was important to provide supplementary material that provides background for the instructors to use so that they feel confident using the teaching modules. This includes references, a lot of in-depth background information on the topics, discussion questions and answers to those discussion questions, as well as in-class exercises and answers to those exercises. In addition to that, we do provide you with the PowerPoint slides that are annotated. So you don't have to develop your material, your teaching material from scratch. Rather, you can use the PowerPoint slides and the information we provide you to teach this material in the classroom. And then lastly, there's a homework problem and the solution to the homework problem associated with each of these learning modules, so that students can practice on their own and get feedback on their knowledge and how much how they're doing within the class. All of this is really designed around the concept of the spacing effect. So rather than make a whole new class on structural fire engineering where we provide all this information at once to our students, we're integrating it into the already existing undergraduate civil engineering curriculum. So they get the information throughout their entire undergraduate career. And what the science has shown around learning is that the students will actually learn better when they get a little bit of the information over a longer period of time, rather than inundated with kind of a flood of information at once. This will also allow them to see the context of what they're learning. So as they're learning about material properties for in their strength of materials class, they're actually learning about how those material properties change at elevated temperatures. So you can kind of link the 2 concepts together mentally. So a little bit of background on this concept of structural fire engineering, and that I'm kind of including the prescriptive design within this. A lot of surveys that have been deployed throughout Europe have shown that members of the design team actually are not able to have this level of knowledge necessary to implement structural fire engineering on jobs, particularly since architects are often tasked with being responsible for this, even though the structural engineers are the ones doing the work. So when a lot of architects are asked to define these terms that I'm showing at the top, they're really not able to do so. Yet when we survey architects in the EU, what's found is that while 86% of the architects felt responsible for the fire safety, 65% of the structural engineers are serving as fire protection experts on 65% of the projects. So the structural engineers are serving as these fire experts. The architects are being responsible for the fire safety, but neither are actually being educated in this topic. So this is a massive issue. And so we felt it was necessary to include this in the undergraduate education and curriculum so that the structural engineers have the language to talk, they have the knowledge to be able to implement this on jobs, and they have the knowledge to be able to act as that expert on projects. So let's talk about the teaching modules. So the first teaching module is a mechanics strength of materials teaching module. And this goes over steel material properties at elevated temperatures. Students are already being tasked with testing tension coupons in their mechanics or strength of materials class and developing stress strain curves, calculating the Young's modulus, calculating the yield stress, looking at the shape of the curve. So why not do it at elevated temperatures? So this teaching module actually asks students to take data from tension coupon tests at elevated temperatures, plot it, and calculate all of the material properties. Compare it to those that are published in the AISC Appendix 4. And comment and kind of understand and look at how the shape of these curves are going to change with elevated temperatures, and come up with all of the concepts of, you know, what is happening to steel as it's being heated. The second teaching module has two parts depending on how much the instructor wants to engage in this, and it's really calculating the compression capacity of a column at elevated temperatures. Students can do this at a set temperature, or they can actually do it throughout an entire fire, so as the temperatures are changing. So the students need to have an understanding of the strength of materials. They have to have an understanding of the material properties at elevated temperatures, and then they're gonna go and they're gonna use those material properties. So we're building upon what they're actually learning previously. Usually students are taking strength of materials or mechanics of materials in their second year. At Oregon State, usually students are taking steel design in their fourth year. Sometimes that's occurring in the third year at other institutions. So the last, the fourth steel design teaching module is looking at system level behavior. So building upon what the students are learning in calculating the compression capacity of the column, and then looking at it throughout an entire system. How do forces in the columns and the beams change when the design fire changes? Looking at the impact of those design fires on the force demands in the members. And then the last teaching module is, again, this fire protection design, going over the prescriptive fire protection design, but also going over what are the different types of fire protection and how do they actually work. So this is also really important for students to understand. All right, so these are the 4 teaching modules that include all 3 of these materials here. So we recommend that teachers look at the supplementary material, educate themselves, see what they're comfortable teaching, adapt the lecture PowerPoints to their style of teaching, to what they would like to include, and then there's a homework assignment and answer key. The fire protection design includes just a lecture PowerPoint, it doesn't include all the other material. I did want to acknowledge some people who were really instrumental in helping develop these teaching modules. Nicole Nickerson is a graduate research assistant at Oregon State University, and then there were members of the ASC Fire Protection Committee that were really helpful in developing these. If you have any questions, please feel free to reach out, and I hope that you all use these teaching modules in this coming school year. Thank you.
Okay, so that was our structural fire engineering teaching modules. The next one we have is a virtual reality teaching aid created by Hannah Bloom, assistant professor at University of Wisconsin-Madison. Hannah is actually here in our workshop today, so she can probably answer any questions that you might have. This one is really interesting because Hannah actually approached us a few years ago looking to see if there was possibly a building under construction that we could connect her to, where she could actually film. So she came down to Chicago a few times to capture this footage, and I was able to go out on site with her, and that was a fun experience. So yes, this is our third of 4.
Hello, everyone. I'm Hannah Bloom, and I'm an assistant professor at the University of Wisconsin-Madison. And today I'm going to talk to you about a virtual reality teaching aid. I'm going to give you an overview of a virtual reality tour of a steel building. This has audio of the tour guide, pop-up images to show concepts, and periodic comprehension quiz for some versions. I'm going to go through the details and demonstration, how to access, and suggestions for implementation. Now, one version is the YouTube version. To access this, you need to subscribe to the AISC Teaching Aid Virtual Reality High-Rise Building Tour. You need to ask AISC for this link. It's currently private. You need to log into the same YouTube account that you subscribe to the building tour with on your VR headset through the YouTube VR app. You can view this as a playlist or select individual scenes to play up to 11 scenes. I'm now going to show you a demo where someone is using a VR headset, specifically the Quest, and you are going to see what they see.
Take another look at the 52nd floor framing above you. Do you see the rectangular shaped openings in the beams? These are web openings. You will see these web openings throughout this floor. Web openings are often made to accommodate mechanical ductwork or plumbing pipes. Working with other trades, structural engineers coordinate the locations of these openings in optimal locations along the beam span. Generally, areas of low shear are preferred because a large section of the web is being removed. Throughout the design process, coordination with the architect and other trades is important for a successful project. In high-rises, the teams include experts in mechanical, electrical, plumbing systems, and vertical transportation, aka elevators. On the south side of the building, a staircase connects the 51st floor to the 50th floor below us and to the 52nd floor above us. These stairs continue all the way down to the ground level for egress. Here, the steel frame stair uses steel drop-in stairs. Stringers serve as the main load-carrying members, and the stringers are channel shapes. The channels span from supports, which can be floor framing members, concrete embeds of a shear wall, or steel rod hangers. Stairs are often delegated design.
I hope you liked that excerpt of the video. Please note this tour is the same for all versions. I just showed you the version that was from YouTube. Another version is through the Oculus Go store. For this, you download from the Oculus store, and the store can be accessed through the Oculus app from a phone or tablet. Please note this is only for the Oculus Go headset. After the tour, you can move around freely to explore your own time without replaying the explanations. I'm now going to show you a demo of someone using a Go and moving around the building after the tour is finished. So moving around on their own just to review some of the scenes. Please note you are seeing what the user sees, but this is streaming to a phone and the phone screen is being recorded. This is the only way to show videos on the go. Here we are moving around the building to locations where the camera was placed. So you can see now we do not have to listen to any explanations. We can just move around freely on our own after the tour is completed. Another version is the web version. This can be found online. This has some quiz questions after certain scenes. As you can see here, we have question 1, question 2, and question 3. These are comprehension questions to help the students assess if they have understood the explanations. You can only view this on a flat screen. It's not immersive like in the VR headsets. You can access this from a VR headset through the web browser, but you are still going to see it on a flat screen. To move around, when you're in the scene, you would click and drag with your mouse. Feel free to try this out on your own time. If you see the cards here, the blue, you click on that to access the recording for that scene, and the white to access the scene only. Another version in development is for the Oculus Quest. There's a slight software issue which we are trying to work out. When this is finished, we will have quiz questions in this app, and this will run only on the Quest headset. Now you might be wondering, how do we implement this? If you're planning on getting a VR headset, I recommend the Oculus Quest 2. Each one's about $300. It's the cheapest you can get and pretty good quality. You also need a tablet to manage the fleet. Many universities have a technology group to manage the equipment. I recommend you use this route. It will save you a lot of time. If you have a Quest, the first priority would be to use the Quest app that we are planning on releasing after we work out the software glitch. This will have the best features for you to use. If not, you can use the YouTube version. Note the YouTube version does not have the quizzes embedded. The Oculus Go is no longer sold. If you have a Go, I recommend you use the version from the Oculus store that will give you the best performance. If you have another VR headset, not listed above, use the YouTube version. If you don't have a VR headset and don't plan on getting any, use the web version. So how can we implement this? AISC will explain how to access the VR files, either the web or YouTube platforms or through the Oculus store. We also have a quiz for students to take after the tour. My research group's currently using this quiz for an engineering educational study. So after we have finished with our study, we will gladly share the quiz and the solutions for you to use in your own class. I want to give a special thanks to the VR building tour team, especially to PhD student Ed Sippel, who has helped a lot with this development, and also to thank the AISC education group. I also want to give you a brief preview of a newly developed building plan matching game. This is meant to help students read plans by correctly selecting the identification of several members throughout the structure. The plans can be viewed in the game, as well as hints and other useful information. More details on this can be presented at a future venue. This concludes the presentation.
Okay, and since we have Hannah here, I was wondering if anyone had any questions on this particular teaching aid. Okay, if there are none, we'll move on to the next one. Here we have a 3D-based model viewer that was created by Mark Denovit. He started out with a module on connections, and now he's updated his suite to include buckling modes.
Hello, everyone. I'm glad to be able to speak to you virtually about the teaching aid that I developed for AISC. Before I introduce the aid itself, I want to describe its inspiration. I see too many errors like this in my introductory steel design course, where the students subtract out 2 holes to get the net area when they should only subtract out 1. When the students are starting out, they don't necessarily have a feel for what the drawing is representing or the limit states they are calculating. They may have never seen, up close at least, a steel angle, let alone one with holes drilled through for bolts. All the necessary details are there in the 2D drawing, but the important cross-section is perpendicular to the page. and that's a jump. Two-dimensional representations are no doubt useful, but they are often not a good substitute for the three-dimensional reality for folks that are just starting out. This is not just true for connections. Buckling is another area where I sense that students have a difficult time visualizing what is happening. Physical models work great to bridge these gaps, but you can't always lug them around, which means they aren't always available when you need them or when it would be most beneficial for the students to have them. And that brings me to the three-dimensional model viewer for illustrating structural steel concepts. Three-dimensional digital models are a pretty good substitute for physical models, and this website makes it easy to use them in a steel design course. Just navigate through the AISC Teaching Aid website or go to the URL shown in red. You can use your computer or smartphone. What you'll find are sets of collections. Initially, a set of 4 collections was developed on tension member connections. With a follow-on project, we developed 4 more collections on buckling. Each collection has several three-dimensional models plus more related content. The connection collections have 2-dimensional drawings and calculations. The buckling collections have commentary. Both have more fun pages with interesting facts and questions for further exploration. The models are designed to each highlight an important feature of behavior. This collection of a WT connection has a set of models that show 3 different block shear rupture failure modes. And they're not just static images. You can rotate and zoom these on the website. I would show that to you if I had better video editing skills. This collection features multiple possible buckling modes for a braced wide flange column. We have lateral torsional buckling, flange local buckling, shear buckling, and more in the I-shaped plate girder collection. I plan to use this teaching aid as a visual aid in lectures. We'll try and avoid attempts at 3-dimensional drawings on the whiteboard. I also think it'll be very helpful in office hours for explaining net area and other concepts in a one-on-one setting. I also imagine that students are going to use this on their own. It's going to be there when they need it most, working on homeworks or studying for exams. With that, I'd like to quickly thank those who have contributed to the development of this teaching aid, namely my PhD student Peter Talley, as well as others at the University of Tennessee who developed the website. Several members of the review committees that AISC put together to provide valuable feedback on this work, as well as AISC itself for funding the development of this project. Before I go, I would also like to note that we built the site to be extensible. Directions for contributing are also on the website. Thank you for your attention, and I hope you find this teaching aid useful.
Okay, those are our four of our newest teaching aids. It looks like we're kind of running short on time. I was going to do a breakout room, but instead of that, does anyone have any favorite teaching aids that they've been using, or any resources from AISC that you want to encourage your fellow faculty to use, excuse me? It looks like we have a chat that came in from Jenny that there are a lot of papers posted in ASEE that also have a lot of great ideas. All right, and now I'll just open it up to some general discussion. I just have a few closing announcements, but if there's anything that we didn't get a chance to address, if you have any other questions, go ahead and ask. It looks like there's a question from from Hannah to Ron about how you handle grading your math stand items.
Sure. Thanks for the question. Pretty much what I've done now is I've got the students working in pairs of 2 to complete each one of the modules. So they're working together to gather the data. But similar to Erica Fish's learning modules, and there's a series of questions that sort of tease out their thinking. And so I have them do those individually, but then review each other's solutions. So I'm not, it's, it is certainly graded, but I'm really trying to get each one of them to have a good positive experience. So I'm not, having them compete against each other for the best grade in the class, but sort of working together to see how it goes. And like Mark Danovitz's more fun section, sometimes I'll have this challenge to students to try to answer one of the more fun section questions, which were really intended for those that want to use the learning modules in the graduate school. But like I said, Katie's on the line. She might be able to answer how if she does any of the grading or that as well. Thanks.
Okay. Any other questions? Anything else?
I did want to say, I meant to mention in the hands-on demo part that Matt Yarnold and Ryan Sherman given an assignment in their class for their students to create hands-on demos, either like a new one that they haven't used in class to help illustrate a concept or to improve on one. I think Ryan is with us. Ryan, do you want to elaborate on that?
Hi, yeah, I got the idea from Matt Yarnold to go ahead and I used a lot of the demonstrations that were presented today, and the students are creative. So if you give them an opportunity to improve on a demo that you did or come up with a new demo from a concept they're struggling with, I put them in groups of 3 and saw what they came up with. Matt told me the cool things he had them do. I think someone used a 3D printer to eventually create a steel section from like the rolling process. So that was pretty involved. I know Matt Hebden recently also did it at a graduate level course, and I think he allowed them to do either something at the undergraduate level or at the graduate level, because by that time they should have had concepts from either side of those courses. It was really a fun thing for the students. They presented it at the end, and the big caveat was that I got to keep the demo at the end of the project, because it was kind of this idea that you can pay it forward to your future students, that, hey, this helped you learn, let's help the next set of students coming through this course learn as well.
All right. If there are no other questions, any final comments from Judy, Ron, or Larry before I wrap up?
Just want to say thank you to everyone for joining us today. It's been great to share this time, and look forward to further discussions and interactions to see how you're developing innovative approaches and materials for your own classes.
Couldn't have said it better. Thank you, everyone.
Yeah, likewise. Thank you, everyone. And especially thanks to AIC. I mean, they've really come a long way with their partners in education, and all these tools that are now available and funding projects to do this. It's just really exciting to be part of it. Really hope to see you folks next spring in Denver. The AIC has these teaching workshop, teaching meeting, usually the first day of the conference, and it'd be nice to meet all of you at that time. So, but have a good semester. Nice speaking with you.